This video is all about determining the number of valence electrons you expect to find in an atom. Now, one of the things about this that's kind of cool, kind of simple actually, is that you need to understand that you're actually not really talking about all of the elements here when you're doing dot configurations. These guys here, the transition metals and the inner transition metals, all right, we're not going to do the dot configurations of them. They're a little different. What we're going to do instead is we're actually going to deal with the representative elements. Now, the representative elements are the guys, they're the ones that are filling the s and the p orbitals. And one of the reasons why they're called representative elements is you have pretty much a representative of every kind of element there is. Okay, you have metals, you have nonmetals, you have gases, you have liquids, you have solids, you have Nobel gases. So you have a little bit of everything in this group. So they don't have a tendency to act the same. Now, one of the things about the representative elements is you can automatically tell how many electrons are in the orbital by how far across the periodic table they are. Okay, remember, when you're doing the periodic table, when you're filling up the periodic table, what you're really doing is you're putting more electrons in each orbital as you go across. So, for instance, in the first row, there's only 2 electrons, so therefore, there's 2 slots. It's the s orbital. There's only room for 2, so there are only 2 elements in that row. The next row, there's actually room for 8 elements because you have the 2 s's and then the 2 p's, which is 2 and 6 is 8. The next one has 8. And if you actually ignore these transition metals, it goes all the way down that the guys who are in each orbital, okay, all right, has that number of electrons, okay? Now, they conveniently usually label this, but you don't really need to have the labels. If you actually take a look, you notice that in Roman numerals, this is a Roman numeral 1, there's 1 electron in that orbital. Roman numeral 2, there's 2 electrons in that orbital. Roman numeral 3, 3 electrons. Roman numeral 4, 4 electrons. Roman numeral 5, 5 electrons. Roman numeral 6, 6 electrons. Roman numeral 7, 7 electrons. And the last one, which is 0, is 8 electrons. All right. So if you look down and you actually take a look at the problem, you can tell that that's the number of electrons that each one of these is going to have. You can also, if you don't have the numbers there, you just conveniently count the representative elements. This is going to be 1, 2, this is the 3rd row over, 4th row over, 5th row over, 6th row over, 7th row over, 8th row over. And that's the number of electrons they're going to have in it. Okay, that's basically all you really need to know to do this particular little problem. Now, why are we doing it? Well, it's not really that exciting right now. But what you're going to find out when you do this is a handy way of telling how many valence electrons there are in an atom. And then knowing that, you're going to be able to tell how that atom reacts. Okay? So if you actually take a look at this, the first choice here, number A, that has 1 electron. Those are all going to be the guys in the first column. Those guys are going to be, any guy who's in that column is going to have A electron configuration. These blue guys, beryllium, magnesium, calcium, strontium, barium, rubidium, they're in the second column. They're all going to look like B. 3A, boron, and then aluminum, gallium, the purple guys. Okay, those are all going to be C's, blah, 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 so forth and so forth, until you get to orange. And those are the guys who have the H configuration. Notice there's no room there. There's no place, there's no empty, it's not missing any electrons. That's a very important fact. That's why those guys don't react, because everything's full. All right, so let's take a look and just try a couple of these, and then I'm going to put you on your own. What is the valence electron configuration for oxygen? Well, if I look up here, I notice oxygen is right here. O is this here. And if I count across, it's lithium, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6. So it's going to have 6 electrons in its outermost orbital. So all I have to do is look, and it's F that has 6 electrons, so I'm just going to choose that. Boom. 6 electrons. All right, now valence electron configuration for hydrogen. Hydrogen in the first row, that means it has 1. A, the choice shows a configuration with only 1 electron, so I choose A, and that's how I do this, so forth for the whole thing. All right, now will tell me exactly how many different electrons on the valence orbitals. Okay, That's it. Get this one done, and you should be able to do very, very well on the test.